Example 2.2, a sample of gas expands from 1 to 4 cubic meters, while its pressure decreases from 40 pascals to 10 pascals. A, rank the heating, workings, and internal energy changes for processes A, B, and C. Greatest first. Now draw an energy bar diagram for each process. B, how much work is done by the gas if its pressure changes when the volume via path A, B, and C. Does this agree with part A answer? Since internal energy only depends on the endpoint, in other words, it's path independent, all paths have the same change in internal energy. Now, to make it a little bit easier, I'm going to define two additional states. So if I look at my graph, I'm going to look at it and it's going to go like this here. So I'm going to have, I'm going to go so here's my 10, 20, 30, 40, 50. And all of these are in units of pascals. And then I'm going to have my volume. So then if I call this 0.1, and then my volume goes to, let's say, 1, 2, 3, 4, this right here is 0.2, then you could see here that I have path A. So path A is going to come along this path. I'm going to call this point right here 3. So that's one of the new states. And then I'm going to have a second path. And this is path C, which goes from here to here. And I'm going to define this second point 4. So now when I look at the middle path, you could see here that this guy's just a straight line going to right here. And this path here is what we call B. And this path here is C. So now that I've done that, what I'm going to do here is to get a sense of how, whether there's an increase or decrease in internal energy, I'm going to start by determining the temperatures and ranking them. Okay. And so here I go. I know that the ideal gas law says that the pressure times the volume is proportional to the temperature. And I know that the temperature is proportional to the internal energy. So I'm going to use that. So here I go. So I'm going to look at, I have states. So now I have 4 states. I have 1, 3, and then I can go 1, 4, and then 2. And then I'm going to write this in PV in units of joules. So all I have to do now is just multiply the pressures times the volumes. So this guy right here is 1.0, and this guy is 4.0, and this volume is in meters cubed. So if I look at 0.1, it's going to be 1 times 5, so that's going to give me 50 joules. If I look at 3, it's going to be 50 times 4, which will then give me, right, it should give me 200, right, 50 times 4. And then if I look at 0.4, it's going to be 1 times 10, so that's going to give me 10, and then I'm going to have 10 times 4, which is going to give me 40. So just by setting up this little table, this is telling me about the temperatures. So now I can immediately state that I could then see that T1 is greater than T2. So this implies here that the internal energy at 1 is greater than the internal energy at 2. So that means here is that there's a decrease in internal energy for all paths. Okay. So now if I look at how the temperature is changing here, so right away, I'm going to say, so physically, this really helps me look at the picture now as I move on. So now I'm going to rank all of them. So just by looking at this, you could see if I look at path A, I immediately see that I'm going to go, that I see that I'm going for what? The highest temperature is T3. And then if I compare 1 to 2, you could see here that that's T1 greater than T2. I'm going right off the table. And then if I look at path C, that's going from 1 to 4 to 2. And you can see if I compare 1 to 4 to 2, the rankings are is that the temperature is 1 greater than 2 greater than 4. So I now have all of the temperature rankings, which then also tell me the internal energy rankings. So now what I'm going to do here is that I'm going to look at that cycle right there, and now I'm going to set up a table to list the signs of Q, W, and change in internal energies. Okay. So I've already created it, and I'm just going to paste it right here. So I'm going to leave it right there. So now that I have that, I'm now going to just start working my way through it. So here I go. So I'm going to start with the blue path. So this is path A. And we know that this goes from 1 to 3 to 2. So here we go. So now let's go through the process. So I need to talk about the heating, the working, and the internal energies. No, we already know the internal energies because we already computed the temperatures. So here I go. So the first thing I'm going to do here is I'm going to look at my heating, my workings first. So the first thing is that I'm going to look at the working. So what I see here is that I see this here. So actually, that's not the way I want to do it. I'm going to break it up into paths. So I'm going to say, I'm going to do 1 to 3 first. So if I do that, then here's what I see. The easiest thing to do is look at the work. You could see that the piston expands. Which then implies that the microkinetic energies decrease. Because so that means then that therefore the work from 1 to 3 by the gas molecules is negative. So now what I'm going to do next is that I'm going to look at the heat. So if I look at the heat, note that to keep pressure constant, as this thing with increasing volume, that immediately tells me is that K micro increases. And if it increases, that means that the heat from 1 to 3 must be positive. So I'm going to come in here right away, and I could see that from 1 to 3, this is positive, this is negative. And then the next thing here, what about the internal energy here? Well, if K micro increases, it automatically tells us that there's an increase in internal energy. But if I compare the temperature of 3 to 1, we already see that 3 is higher here. So the fact that K micro increases, that immediately tells us that that T3 has to be greater than T1, even though we already numerically calculated. So then this tells us here is that then the internal energy from 1 to 3 is positive. So there's my signs right there. So now let's go look at what happens along path 3 to 1, 3 to 2, excuse me. So now we go to the second one, and we're going to go from 3 down to 2. So now I'm going to go through the same process. So look what happens. This is isochoric. Isochoric immediately tells us that the work from 3 to 2 is equal to 0. And like I said, it's isochoric. That means that the gas molecules do not change kinetic energy. And then the next thing here is that now we're looking at the heat. Well, if I have the same amount of volume and the pressure decreases, I have to decrease the temperature of the gas. So in this case here, we go from from a higher to a lower pressure implies that K micro decreases. And the only way we can do that is if we pull heat out of that situation. But if I decrease, right? So now again, look at that. So K micro decreases. And immediately, as soon as K micro decreases overall, that tells you then that the temperature at 3 must be greater than the temperature at 2. So therefore, the internal energy from 3 to 2 also decreases. Which of course then tells me that the sign of 3,2 is then negative. So now I can come in and I can put a negative sign here, a negative sign, negative sign here, and 0. So now let's look at path B. So if I look at path B, I'm going from 1 to 2 here. So there's only one path, so I got to go from 1 to 2. So what do I know here? What I know here is that we already know a couple of things. If there's an expansion, then that means that the only way to expand is that the microkinetic energy decreases. So then I'm going to come in here is that because of the expansion, so because of expansion, K micro decreases. And if it decreases, that tells you that the work between 1 and 2 is negative. Okay. Now let's talk about the heat here. When I look at the heat, am I adding heat or am I removing heat? I'm going to say that that's a little bit too hard to say. So I'm going to say that it's impossible without a bar diagram or a calculation. Because of that, I'm going to say that the heating is going to, I'm just going to say that it could be positive or negative just because I don't know. And then if you look at the internal energy, we've already agreed that the temperature at 1 is higher than the temperature at 2, so therefore it has to decrease. So since T1 is greater than T2, that implies that there's a decrease in change in internal energy from 1 to 2. So that, of course, tells us that is a negative sign. So if I come back into my table, I know that the gas loses energy. I know that the overall internal energy is, and then here, I'm going to say that this could either be positive or minus, just because we don't know. So now let's look at the next case here. And I think I'm going to take this graph down so that it's easier for us to read it. So let me go down to here, and I'm going to bring this, and I'm just going to plop it over here, just so that we can read it here. So now we are moving in path C. So here's path C, and here we're going from 1 to 4 to 2. So there's 2 parts to the path. So the first path we can see here is that we go from 1 to 4. Note that that is isochoric. So the fact that this is isochoric, that immediately tells me that the work from 1 to 4 has to be 0. Now let's look at the heat. The fact that I go from a higher pressure to a lower pressure means that the only means of decreasing the pressure is that I have to take energy out. So in this case here, I'm going to say then that, here, let me modify this a little bit, because I'd rather do it this way. So then I'm going to say this is, so that what the work. So now if I look at the heating, what has to happen? So now again, I'm going from a higher to a lower pressure. So that means here is that I have to decrease. So K micro has to decrease. And the only way we can decrease it here is that if I take heat out of the system. So that's got to be negative. But then again, if K micro decreases, that again tells us that then the internal energy from 1 to 4 must decrease. And again, the temperature of 1 is greater than the temperature at 4. So I know my signs from 1 to 4 here. So if I come up, look what I'm going to do. So if I go from 1 to 4, I know that this is an isochoric process. I'm removing heat, and therefore the internal energy decreases. And then I'm going to go from 4 to 2 now. So when I look at this guy, what's happening? Well, note that I should see as there, because of the expansion here, right? Because of expansion, the gas molecules have to give up their energy. So therefore, K micro decreases. And if it decreases, that means then that the work from 4 to 2 is negative. But then if I look at the heating here, right, to keep P equal to a constant, that means K micro has to increase. And because it increases, that means that the only way that I can do that is that if I add heat in the system. But again, the same type of thinking here. If K micro increases, then that tells me that there has to be an increase in the internal energy from 4 to 2. So now I have my table. So if I come up here, you could see here that I have positive heat, positive change in internal energy, but due to the expansion, I have that. So using my table of the signs for the values here, I'm going to go in and I'm now going to draw the bar diagrams. So here we go. So here's what I know about what I see here. So when I look at my picture here of my cycle here, what you're seeing here is that the greatest work of expansion is has to be less negative than positive. So I would rank the work from 4 to 2 being the largest, followed by the work from 1 to 2, and then followed by the work from 1 to 3. So if I rank my workings here, I would say that the work from 3 to 2, which is also the work from 1 to 4, is 0. And those are going to be the greatest because the work from 4 to 2 is negative, but that's smaller than the work from 1 to 2, which is then even smaller than the work from 1 to 3. So once again, these quantities are negative. And the fact that this guy right here, this one is the most negative. So I'm going to use this to draw my bar diagram for my guides here. So now let's draw the bar diagrams. So the one I'm going to work on first is I'm going to work from 1 to 3 to 2, and then 1 from 4 to 2. So here I go. So this is path A, which goes from 1 to 3 to 2. So note that the work from 1 to 3 is the most negative. So I'm going to try to scale this so that it makes sense here. So I know that there's a decrease in internal energy. Okay. There's a decrease in internal energy, and I should be bringing this down with me so that we can actually see what's going on. So here I go. So the first thing I'm going to do is that I know that I start off with some internal energy, and that internal energy decreases. So I'm going to say that this is my internal energy right here. And this is my internal energy at point 1, state 1. So now here I go. Look what happens. As I go from 1 to 3, I have the most negative work. And that's what the rankings are telling me right there. So I'm going to say that my negative work here is then going to look something like this. It's going to go down, let's say 3 squares. So this will be the work from 1 to 3, and that has to be the largest. Now what I'm going to do is that I'm going to add heat. So what does the heat have to do? The first thing that the heat has to do is that it has to offset the energy of lost by the work. So this is the heat that offsets the work. But then as I go from 1 to 3, there's an increase in energy. So now I'm going to come in and the heating is now more so than the work. So now you're seeing that this guy right here is the heat from 1 to 3. And as a consequence, what you're seeing here is that now there's an increase in internal energy. And you can see that the increase in internal energy increases by 1. So then I'm going to come here. And this shows here that this is the internal energy at 3. But now I'm going from 3 to 2. And I can clearly see that right here, that there is no work from 3 to 2 because that's 0. So the only way I'm going to decrease my internal energy is that I have to take heat out. So look what I'm going to do. I'm going to say that my final internal energy is only 2 squares. So it's going to look like this now. So the only way I can do that is that if I take my heatings and I reduce it by how much? 2 squares. So now this is my heating that I take out of the system from 3 to 2. And that's for path 1. So I think I'm going to move this up higher to save space. So now what I'm going to do is that I'm going to go in and I'm going to look at path C. So now path C goes from 1 to 4 to 2. Now, so I'm going to play the exact same game. So they have to start off with the same internal energy. And you can see here is that here's E1. But now look what happens. As I go down, there is no work for path C. So right away, I could see here is that this is the work from 1 to 4 is 0. But I know I have to decrease my internal energy because it's going to a lower pressure at the same volume. So microkinetic energy has decreased. So I'm going to say here that now I'm going to decrease it. So if that was 3 and this is 2, I'm going to say that this right here is going to be my internal energy at 4. So if I do that, that means then I have to decrease my internal energy by ejecting heat by 2 squares in this case. So then I have the heat from 1 to 4, and you could see that it's negative. So I now go from 4 to 2. Now, no, that work is much smaller than the work from 1 to 3. So when I look at that work should be, let's say it's 1 square. Because it's a lot smaller. So then this guy has to be the work from 4 to 2, which is negative because the gas particles have lost kinetic energy. So now what does the heat have to do? The first thing that the heat has to do is it has to what? It has to kill this thing off right here. Right? That's the amount that does that. And then I have to increase my internal energy. Now note, my final internal energy has to be the same for all states. So when I'm looking at this, you could see that then my heat has to increase this guy by 1 square. So if this is 2, you could see that then I have a net energy change of heat between 4, 2, which then gives me that final internal energy. Look how the internal energies are the same. So now let's go to path B. And this one's just 1 to 2. And this one, what we said was going to be tricky because we don't know what the heat is happening. So let's look at two possible situations. Okay. So in each situation, what do I have? Well, I know that my internal energy starts off like this, right? So I'm going to look at this possible path and this possible path. So here, I'm going to say that this is my internal energy 1. This is my internal energy 1. And all I know is that in the end, what I have to do here is that I have to get to this internal energy right here. Because the internal energies are the same for all states. So in this case, we're going to say that here, we're going to assume that the heat from 1 to 2 is positive. And in this situation, we're going to assume that the heat from 1 to 2 is negative. Now, let's rank the works now. So what do I know about the works? We know that the work from 1 to 2 is mid-size. So look at that. So this one is 3 squares. This one is 2 squares. So that means the work has to be in between. So I'm going to say that the work here has to be 2 squares no matter what. So this is the work from 1 to 2 because of the expansion. Now, what I'm doing here is, as a guide, I note that the work from 4 to 2 is greater than the work from 1 to 2, which is greater than the work from 3 to 1. So then the question is, if I do heating, so note that if the works are the same, look what has to happen. So if I add heat here, which is the heat from 1 to 2, I could set this up in a way that I'm going to have a reduction of 1. So again, you're seeing here is that here I add heat. But because of the way the work is, if I try to add any kind of heat, regardless of what is actually happening, you're seeing that I could never get to that same final state as when I'm removing heat. So here, I remove heat. So what this tells me here is that the only possibility is adding heat. Okay, so once again, so if I try to summarize how this does that, so because the working from 4 to 2 is a fixed quantity, is a fixed quantity. Oh, wait, not from 1 to 2, excuse me. 1 to 2 is a fixed quantity. It appears that removing heat is impossible. So the bar diagram actually showed us how to do that. So now we're at the end here, and our job here now is to do what? We need to go in and we need to calculate the works. So it says here now how much work is done by the gas. So let's go do that now. So here, we're now at part B, where we want to determine numerically, all the workings. Okay. So here's our graphs. So what I'm going to do is I'm going to paste this right here. And then I'm going to use this process to actually do that. So I'm going to keep using this graph as a guide here. So here I go. So what I'm going to do here is that this is going to be the work along 1 to 3 to 2. Okay. So I'm going to take this and I'm going to move it over here. And so if I do that, then what I'm really seeing is that none of these paths exist at all. Right? None of them exist. So what you're seeing here is that the work is the area under the curve. So in other words, this is the whole area under the curve. So because this is the area under the curve, I can compute that. So then, here we go. So the work for path A has to be the work of 1, 3 plus the work of 3, 2, but because this is isochoric, that's 0. So then this really tells me, now remember, this is a negative work. Why? Because the kinetic energy of the gas molecules decreased. So I have to come in here by hand and put in that negative sign. So that should be the change in pressure from 0.1 relative to 0, and this will be the change in volume from 1 to 3. So if I look at this numerically, it then now reads what? It's going to read minus, then I'm going to get 50 minus 0 times 4 minus 1, and this is going to give me negative 150 joules, and that's the work of A. Now, let's do the exact same thing for the work of B. So this is the work along 1, 4 to 2. And this is path B. So if I look at this guy here, it looks like this. So the only path I care about is this path right here. Right? I don't care about any of the other paths. Let me make sure I did the, so this is the, so if I look at this path, you can clearly see here, and that in this work, this is the work of B, oh no, of C, excuse me. This is going to be equal to what? The work from 1 to 4 plus the work from 4 to 2, but because this is isochoric, that's 0. So when I compute this, note that this will then be minus the change in pressure from 0.4 to 0 times the volume change between 4 and 2. So if I compute that, then I'm going to get, again, remember, I have to put in that minus sign by hand. This is going to be what? 10 minus 0. And then I'm going to have 4 minus 1. So then I'm going to get minus 30 joules for the work of C. And so finally, I'm going to do now the work from 1 to 2. So let's put that in there. So that only is the green line. So that means I'm going to take this out. I'm going to take this out. And that's what we're talking about. So if I look at this area, here's what I see. The area under the curve looks like this. So what you're seeing here is that there are two areas. There's this area, and then there's this area of the triangle. So what you're seeing here is that, note, we've already computed this work right here, right? So if I go in here, note that this work, we've already computed that work, and that work is essentially the work of C, which is minus 30 joules. So what I really need is I need that triangle. Okay, so here I go. So then that means here is that then the work of B is really two pieces. There's the triangle plus the little rectangle. So if I look at that triangle, I'm going to treat this as, it should be what? It should be minus 1/2 the rectangle, which would then be the pressure difference, right? So that's going to be the pressure difference between 1 and 2 times the volume change from, what is it? 4 to 2. Plus, remember, there's really a negative, the work of C. So if I compute that, here's what I'm going to get. So this guy's going to be minus 1/2, and then I'm going to get what? The pressure difference here is going to be 50 minus 10. The volume is going to be 4 minus 1, and then I'm going to get minus 30. So if I compute that, I'm then going to have what? I'm going to have 40 times 3, that's 120. Let me make sure I get that right. That's 40 times 3. So this should be minus 1/2. 40 times 3, that's 120 minus 30. So then that should be minus 60 minus 30. So this should give me a value of minus 90 joules for the work of C. So now, if I compare my rankings, so the numerical rankings are that the work of C, which is equal to minus 30 joules, is definitely bigger than the work of B, which is minus 90 joules, which is definitely bigger than the work of C, which is minus 150 joules. So this agrees with what we got conceptually.